In exactly 48 hours, something remarkable will occur. An object hurtling through space at 137,000 miles per hour, launched from another star system, will pass within 29 million kilometers of Mars. What makes this moment extraordinary isn't just the encounter itself, it's what this visitor might represent. Harvard astrophysicist Avi Loeb has assigned it a 6 out of 10 on his scale for potential technological origins. That translates to 60% confidence that what we're observing isn't entirely natural. When amateur astronomers began capturing images of this object, the scientific community found itself grappling with questions that challenge our understanding of what comets should be. This isn't behaving like any comet we've documented before. It's releasing pure nickel without iron, a combination that doesn't occur in natural cosmic processes, but does appear in industrial manufacturing. Its chemical composition is 16 times more extreme than any known comet. It transformed from red to green seemingly overnight, and its trajectory carries odds of 1 in 500 of being random. But there's a complication. In late September, 3I Atlas disappears behind the Sun for 2 months. We won't be able to observe it during its closest approach on October 30th. Some researchers suggest this timing could allow for activities we wouldn't detect, perhaps even the deployment of smaller objects too diminutive for Earth-based telescopes to resolve, objects that could reach Mars while our attention remains fixed on the primary body. Over 227 observatories worldwide have tracked this object, compiling more than 4,000 observations. Every data point adds another layer of strangeness. At 33 billion tons, it exceeds statistical expectations. Based on what we know about interstellar space, we should have discovered roughly 100,000 smaller objects before encountering something this massive. So what is 3I Atlas? In the coming half hour, we'll examine every anomaly, every observation, and every theory that challenges conventional understanding. Because after October 3rd, when Mars spacecraft turn their instruments toward this visitor, we might finally approach answers. Avi Loeb has sent ripples through the astronomical community. The Harvard astrophysicist who suggested Oumuamua might carry technological origins back in 2017 has now rated 3I Atlas at 6 out of 10 for potential artificial characteristics. This isn't speculation driving his assessment, it's data from humanity's most sophisticated instruments. The James Webb Space Telescope, the Very Large Telescope in Chile, and Hubble have all captured observations that defy conventional models. Webb examined 3I Atlas on August 6 and discovered its gas plume consists of 95% carbon dioxide and only 5% water. That ratio is 16 times more extreme than any known comet at comparable distances from the Sun. Comets are supposed to be water-rich, frozen remnants from the outer reaches of planetary systems where water ice dominates. This one inverts that expectation entirely. Then the Very Large Telescope detected something more perplexing: nickel in the gas plume. Clear, unmistakable emission lines, but with no corresponding ion signatures whatsoever. In the entire history of observing celestial objects, nickel and iron have always appeared together. They're forged simultaneously in the nuclear furnaces of dying stars and expelled together in supernovae. Their cosmic partnership is fundamental. Finding nickel without iron resembles finding smoke without fire. It simply doesn't happen through natural processes. Yet it happens constantly in human industry. High-purity nickel alloys for aerospace applications, electronics, specialized batteries. The spectroscopic signature we're detecting from 3I Atlas matches industrial production patterns, not natural cosmic abundances. The nickel emission is also intensifying. When first detected in July, the rate was modest. By August, it had exploded 25-fold. The closer this object approaches the Sun, the more metal it appears to vaporize. Loeb has faced considerable criticism for entertaining extraterrestrial explanations. Penn State's Jason Wright called his approach sloppy. NASA's Tom Statler insisted it resembles a comet and behaves like one, but neither has explained the nickel without iron. Neither has addressed the extreme carbon dioxide ratio or the trajectory with 500 to 1 odds. Loeb himself acknowledges his technological hypothesis remains largely an intellectual exercise. He maintains the most probable explanation is still a natural comet, but most probable carries an important distinction from certain. With a 6 out of 10 rating, He's suggesting a 40% chance that conventional models fail to capture what we're actually observing. The October 3rd Mars flyby promises additional clarity. If the high-rise camera reveals a nucleus larger than 5 kilometers, as his mass calculations suggest, the natural explanation faces serious challenges. There simply isn't enough rocky material distributed through interstellar space to deliver objects this large with the frequency we'd require. Social media platforms are alive with something professional astronomers approach cautiously. Amateur astrophotographers are sharing images of 3I Atlas that don't match typical cometary appearance. Instead of the expected fuzzy, diffuse glow, some photographs reveal structure, geometry, and defined edges that shouldn't exist. Michael Yeager and Gerald Rayan, two highly respected amateur astronomers, captured 3I Atlas during the total lunar eclipse on September 7th from Namibia. Their images showed the object glowing green with a bluish quality, clearly gas-rich and visible across multiple filters. Professional astronomers have acknowledged these images as legitimate observations. But other amateurs, names absent from official press releases, have captured what's now circulating as the structured images. Photographs appearing on Reddit, Twitter, and astronomy forums show something more solid, more defined beneath the gas envelope. Something that resembles an object with distinct boundaries rather than a diffuse cloud. The professional response has been silence or immediate dismissal. When pressed, astronomers cite motion blur, exposure artifacts, telescope tracking issues, all technically valid concerns when imaging fast-moving objects thousands of times fainter than naked eye visibility. Smearing and distortion are genuine problems in such observations. Yet here's what makes the situation intriguing. The Atlas Survey telescope that discovered 3I Atlas measures only 20 inches in diameter. That's backyard astronomer scale. Advanced hobbyists possess equivalent or superior equipment. When observers with comparable instruments capture unusual structure, why the automatic rejection without investigation? On astronomy subreddits, debates rage. Users compare images side by side. Some display classic cometary characteristics with developing coma and faint tail. Others show features harder to reconcile with standard models. Compact cores, irregular shapes, pixel patterns that don't match point spread functions for stars or comets. Half the commenters attribute everything to image processing errors. The other half demand someone with professional equipment replicate the observations to verify or refute them. That verification isn't happening. Instead, professional astronomers enter discussion threads to discredit claims without offering to examine the coordinates themselves. One widely circulated image shows what appears as a more compact, less diffuse core than Hubble captured. The amateur claimed it was taken with a 14-inch Schmidt-Cassegrain telescope, stacked from 50 individual exposures, standard practice for deep sky imaging. Professional astronomers immediately cited atmospheric distortion, tracking drift, chromatic aberration, anything to explain it conventionally, but none suggested pointing larger telescopes at those same coordinates. None offered to help verify the observation. Here's what amplifies the strangeness. The Hubble Space Telescope image from July 21st showed a teardrop-shaped cocoon of dust with the glow extending ahead of the object toward the sun. That's official NASA data, and it already violated expectations. Comet tails stream behind, pushed by solar wind and radiation pressure. This one pointed forward. Professional astronomers called it interesting, puzzling, worthy of study. When amateurs observe peculiarities during that same period, it's dismissed as user error. Then Gemini South captured images on August 27th, showing the first evidence of a proper antisolar tail streaming behind the object. Between July and August, something changed. Either 3I Atlas began behaving more like a traditional comet, or our viewing angle shifted enough to reveal what had always been present. Most amateur photos claiming unusual structure were captured in that July to August window, precisely when the object was behaving least like a standard comet, when even professional observations showed anomalies. There's another data point. NASA's SPHEREX infrared space telescope observed 3I Atlas in early August and registered it as a point source. No extended coma, no tail, just a single bright point. That's not how comets appear in infrared wavelengths. They typically show extended emission from warming gas and dust. SPHEREX detected nothing of the sort. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter will photograph 3I Atlas on October 3rd using cameras designed to image the Martian surface from mere hundreds of kilometers away. They'll be imaging this object from 30 million kilometers. ESA has already stated they don't expect spectacular resolution. It will occupy less than a pixel in their cameras. But what if the amateurs were detecting something genuine? The October observations might not resolve the question either. We might need something closer, with better instruments pointed directly at this object, without atmospheric interference. The truth is we're navigating with incomplete information. Professional telescopes operate on limited time and strict observation schedules. Amateurs possess flexibility, but less sophisticated equipment. Somewhere in that gap, something unusual is occurring that neither community fully acknowledges. Because if the amateurs are correct, if there exists structure that doesn't match natural comet morphology, then we're not discussing imaging artifacts. We're confronting the possibility that our models of interstellar visitors require fundamental revision. In 2 days, 3I Atlas passes within 29 million kilometers of Mars. That sounds like a comfortable distance. But here's what receives less attention: the minimum orbit intersection distance. The closest this object approaches Mars' complete orbital path around the Sun is merely 2.7 million kilometers. Loeb called this remarkable fine-tuning. When a Harvard physicist selects those specific words, they warrant consideration. The high-rise camera aboard the Mars Reconnaissance Orbiter will image 3I Atlas with a resolution of 30 kilometers per pixel on October 3rd. That's detailed enough to separate the nucleus from its surrounding dust cloud, to measure the actual surface area reflecting sunlight, and to confirm whether this object truly spans 5 kilometers across, as Loeb's latest mass calculations suggest. If it reaches that size, the natural comet explanation encounters serious obstacles. Based on the limited reservoir of rocky material in interstellar space, we should have detected approximately 100,000 smaller interstellar objects on Oumuamua scale before finding something as massive as 3I Atlas. But we've identified only 2 previous visitors, both tiny compared to this. Here's where the scenario becomes genuinely unsettling. Loeb calculated that if 3I Atlas deployed a precursor probe, a smaller scout craft traveling ahead of the main object by approximately 30 million kilometers, that probe could intercept Mars on October 3rd or during the preceding week. Earth-based telescopes cannot detect objects smaller than roughly 100 meters at Mars distances. That's approximately the size limit of all spacecraft humanity has ever launched. Any precursor probe would be effectively invisible to us. The concept isn't as implausible as it initially sounds. If you were designing an interstellar mission to survey a planetary system, you wouldn't send one massive vessel. You'd dispatch a mothership with smaller reconnaissance probes, deploying them ahead to gather data on individual planets, while the main craft follows a safe trajectory through the system. It's precisely how we'd architect such a mission if we possessed the technology. The trajectory of 3I Atlas makes this disturbingly plausible. The object's path requires only a 10 to 15 km per second velocity adjustment during September to reduce its closest approach distance to Mars to 0. For a technological object, that's a trivial maneuver. For a natural comet, it's impossible. The ejection speed of icy fragments from sublimating comets, based on Webb telescope data, reaches only about 0.4 km per second, nowhere near sufficient. ESA's Mars Express and ExoMars Trace Gas Orbiter will also observe 3I Atlas on October 3rd using multiple instruments: high-resolution cameras, spectrometers, particle sensors. These instruments were designed to study the Martian surface and atmosphere, but are being repurposed to characterize this visitor. They'll attempt to analyze the object's volatile activity and composition from 30 million kilometers away. But there's a secondary objective receiving less publicity. HiRISE won't just image 3I Atlas itself, it will scan the surrounding space, searching for anything that might be traveling ahead of the main object, searching for precursor probes. Loeb suggested this explicitly. Use HiRISE to search for objects preceding 3I Atlas that approach Mars closer than the main body. If materials from 3I Atlas reach Mars in October, materials that couldn't possibly arrive through natural sublimation and ejection. That would constitute a technological signature. The timing carries its own suspicion. 3I Atlas reaches closest approach to Mars exactly 1 week before disappearing behind the Sun from Earth's perspective. We receive one clear view with spacecraft at Mars, then the object vanishes into solar glare for 2 months. It won't be observable again until early December. If you intended to deliver something to Mars undetected, this would be the optimal window. Deploy your probe during the October 3rd flyby, while Earth's telescopes observe the main object. Then the mothership conceals itself behind the Sun for 8 weeks, while the probe executes whatever objectives it carries. The Very Large Telescope in Chile has detected something that shouldn't exist through natural processes. Between late July and late August 2025, spectroscopic observations revealed neutral nickel atoms streaming from 3I Atlas. Strong emission lines at multiple wavelengths, clear, unambiguous signatures of nickel sublimating from the object's surface as it approaches the Sun. But there was no iron, not a trace. 0 emission lines in any of the expected wavelengths where iron should manifest. Let me clarify why this is profoundly anomalous. Nickel and iron are cosmic twins. They're forged together in identical nuclear reactions inside massive stars. When those stars explode as supernovae, nickel and iron are expelled together into space. They condense into dust grains together. They incorporate into asteroids and comets together. In every space rock humanity has analyzed, whether meteorites that fell to Earth or samples returned from missions, nickel and iron appear in predictable ratios. Finding one without the other resembles discovering hydrogen without protons. It contradicts the fundamental chemistry governing universal processes. The VLT team, led by researchers with no connection to Loeb's more controversial claims, published findings with carefully worded conclusions. They suggested the nickel might originate from nickel-carbonyl compounds, molecules that could theoretically exist in extremely cold interstellar environments. These compounds are volatile, breaking apart when exposed to ultraviolet light to release nickel and carbon monoxide. But even the VLT team acknowledged this would be unprecedented, never observed in any solar system comet, never detected in interstellar space, a purely theoretical explanation for an observation that demands one. The nickel production isn't stable. When 3I Atlas was first observed at 3.9 astronomical units from the Sun in July, the nickel emission rate measured around 10 to the 21st atoms per second. Significant but not alarming. By late August, at 2.85 astronomical units, that rate had increased 25-fold. The closer this object approaches the Sun, the more dramatically its metal emission intensifies. That increase doesn't follow the gradual curves observed with normal cometary outgassing. It's exponential, steep, as if something is being systematically vaporized by increasing heat. Loeb articulated what others hesitated to state explicitly. On Earth, we separate nickel from iron routinely in industrial processes. High-purity nickel finds use in specialized alloys for aerospace applications, electronics, batteries, anything requiring specific thermal or electromagnetic properties. The signature we're detecting from 3I Atlas matches industrial nickel production, not natural cosmic abundances. Critics immediately objected. They accused Loeb of cherry-picking data, engaging in motivated reasoning. Penn State's Jason Wright was particularly harsh, calling the comparison to industrial processes misleading and unscientific. But critics aren't addressing a fundamental question. If the nickel originates from natural carbonyl compounds, where's the iron? Iron forms similar volatile compounds. Iron pentacarbonyl is well studied in chemistry. If conditions existed to create and preserve nickel carbonyl through billions of years in interstellar space, those same conditions would generate iron carbonyls. Both should be present, only nickel appears. The VLT observations also detected rapidly rising cyanide production, hydrogen cyanide and related compounds appearing in the gas plume at rates that increase steeply as the object approached the Sun. Loeb suggested the color change from red to green that amateur astronomers observed might connect to this cyanide spike. Cyanide itself isn't unusual in comets. It's a common carbon and nitrogen compound found in many icy bodies, but the rate of increase, the steep production curve matching the nickel emission, suggests these processes link somehow. What's genuinely fascinating is what this reveals about the object's composition. If most mass exists as carbon dioxide ice with trace water amounts, as Webb discovered, and if the surface outgasses nickel and cyanide at increasing rates, then we're examining chemistry that doesn't match anything formed in our solar system. Comets from the Oort cloud or Kuiper belt are water-rich because they formed in regions where water ice was stable. The ratio of water to carbon dioxide reflects the temperature and composition of the protoplanetary disk where they originated. 3I Atlas inverts that ratio, Co2 dominant with minimal water. That suggests formation in a vastly different environment around a fundamentally different star. Or it suggests it's not natural at all. In late September, 3I Atlas vanishes. Not destroyed, not deflected, simply hidden. It passes too close to the Sun from Earth's perspective to observe. For 2 months from late September through November, ground-based telescopes lose line of sight completely. The object disappears into solar glare. The timing carries its own intrigue. 3I Atlas reaches perihelion, its closest approach to the Sun, on October 30th, 2025. That's the moment when comets exhibit peak activity, when solar heating drives maximum outgassing, when their behavior reveals the most about composition and structure. The single most crucial observation window for understanding what this object actually is. And we cannot see it. Earth will be positioned on the Sun's opposite side. Loeb has suggested this could be intentional, not random orbital mechanics but deliberate positioning. If 3I Atlas wanted to avoid detailed Earth-based telescope observation during its brightest, most active phase, this trajectory accomplishes precisely that. It conceals itself behind 150 million kilometers of incandescent plasma at the critical moment. NASA and other space agencies are attempting workarounds. The Parker Solar Probe, currently in close solar orbit studying the Sun's corona, might glimpse it if timing aligns. The Solar and Heliospheric Observatory, SOHO, which monitors the Sun continuously to watch for coronal mass ejections, will have 3I Atlas pass through its field of view. But SOHO's cameras were designed for solar observation, not faint comets. The object will likely be too dim against the Sun's overwhelming brilliance. Jupiter Icy Moons Explorer, JUICE, is currently on the Sun's far side relative to Earth, using its high-gain antenna as a heat shield, which limits data transmission. JUICE will attempt observations in November using cameras and spectrometers, but we won't receive that data until February 2026, months after the fact. We're effectively blind during the most critical period. October 30th unfolds behind a stellar curtain. What could occur during those 2 months? If 3I Atlas is natural, nothing unexpected. It heats, outgasses more intensely, possibly fragments if thermal stress fractures the nucleus, and emerges in December slightly smaller and less active as it heads back toward interstellar space. But if it's not natural, if any technological component whatsoever exists, those 2 months represent the perfect window for activity we're not meant to observe. Orbital corrections, probe deployments, trajectory adjustments, anything requiring propulsion or maneuvering that would be obvious to Earth-based observers if we could witness it. Loeb calculated that a velocity change of just 10 to 15 kilometers per second during September or October could alter 3I Atlas's trajectory significantly, enough to deliver payloads to Mars, Venus, or even Earth. For a natural comet, that's impossible. Sublimating ice produces velocity changes of perhaps half a kilometer per second at most, but for something with propulsion, it's trivial. The other possibility proves more unsettling. What if the disappearing act is literal? What if 3I Atlas doesn't emerge in December? What if it uses the perihelion passage to shed velocity, fall into a long elliptical orbit around the Sun, and become a permanent resident of the inner solar system? We'd have no method of knowing until December when it's supposed to reappear. And if it doesn't manifest where calculations predict, if the orbit has changed substantially, that would be a signature of propulsion, of technology, of intent. December 3rd is when ground-based telescopes expect to reacquire 3I Atlas. Amateur astronomers around the world are preparing. Professional observatories are scheduling time. Everyone wants first confirmation of the object returning from perihelion. Everyone wants to determine if it appears different, if outgassing levels changed, if the trajectory matches predictions. Because if it doesn't match, if 3I Atlas emerges from perihelion on an altered path or with different characteristics, that's when even skeptics will need to consider alternatives seriously. Not as fringe theory from one controversial scientist, but as legitimate possibility requiring investigation. A new analysis has astronomers deeply uncomfortable. Richard Clote, Peter Veresh, and Avi Loeb examined 4,022 observations of 3I Atlas from 227 observatories worldwide between May 15 and September 23. They tracked the object's position with extraordinary precision, comparing its actual trajectory to what gravity alone would predict. They discovered something startling. 3I Atlas shows almost no non-gravitational acceleration. Despite massive outgassing detected by Webb and other telescopes, despite losing hundreds of kilograms of material per second, the object's trajectory deviates less than 15 meters per day squared from a pure gravity-based path. That means it's incredibly massive, far more massive than its brightness suggests. When a comet outgasses, the expelled material functions like a miniature rocket engine. It pushes the comet slightly off course. The deviation magnitude depends on expelled mass quantity and the comet's total mass. Small comets with active outgassing display significant non-gravitational acceleration. Large comets with identical outgassing show less. 3I Atlas is expelling enormous gas quantities. Webb measured 129 kilograms per second of carbon dioxide, 6.6 kilograms per second of water, 14 kilograms per second of carbon monoxide. That's substantial. That should produce noticeable trajectory changes. But it doesn't. The deviation falls below detection limits, which means the object's mass must be enormous to resist that rocket effect. Calculations place the lower limit at 33 billion tons, 33 trillion kilograms, with a nucleus diameter of at least 5 kilometers. That renders 3I Atlas 3 to 5 orders of magnitude more massive than the previous two interstellar objects. Oumuamua measured perhaps hundreds of meters across at most. Borisov was perhaps a kilometer. This object is 5 times larger in diameter, which translates to over 100 times more volume and mass. Based on what we understand about interstellar space, based on surveys of rocky and icy material quantities existing between stars, objects this large should be extraordinarily rare. So rare that we should detect roughly 100,000 smaller interstellar visitors before encountering one as massive as 3I Atlas. But we've found only two, just two previous interstellar objects in all human history. It resembles winning the lottery 3 consecutive times. Statistically possible, but so improbable you begin questioning whether the game is random. Loeb argues this points toward a non-random trajectory. If 3I Atlas was deliberately sent to the inner solar system, if its path was chosen rather than random, then the statistical problem vanishes. We're not randomly sampling the interstellar population. We're being visited by something specific. The James Webb Space Telescope observed 3I Atlas on August 6, 2025, using its near-infrared spectrograph. What it discovered rewrites our understanding of interstellar comet composition. The gas plume surrounding 3I Atlas consists of 95% carbon dioxide and only 5% water. That's 16 times more extreme than expected for a typical comet at that solar distance. Every comet we've studied from our solar system is water-rich. They formed in cold outer regions where water ice was the dominant volatile. Carbon dioxide exists too, but in far smaller quantities. The ratio reflects the temperature and chemistry of the protoplanetary disk where they originated. 3I Atlas inverts that chemistry completely. It's essentially a dry ice ball with minimal water. That indicates formation somewhere vastly different, around a star with different composition, in a disk with different temperatures and pressures, in an environment nothing like our solar system's formation conditions. Martin Cordner, principal investigator for the Webb observations, stated, "This is among the highest carbon dioxide to water ratios ever measured in any comet. Not merely unusual, unprecedented." The chemistry grows stranger. Webb also detected carbon monoxide and carbonyl sulfide in significant quantities. The combination suggests the object formed in an extremely cold environment, potentially colder than our solar system's outer reaches. Some researchers believe 3I Atlas might have originated in a molecular cloud region or been ejected from a planetary system much farther from its star than our Kuiper belt. Then there's the color transformation that amateur astronomers documented. In July and early August, observations showed 3I Atlas with a reddish coma, color typically indicating organic compounds, complex carbon molecules that absorb blue light and reflect red, standard for comets. But on September 7th, during the total lunar eclipse, Michael Yeager and Gerald Rayan photographed it glowing bright green with a bluish quality. The transformation occurred seemingly overnight. Green comets are well documented. The color derives from diatomic carbon molecules in the coma, absorbing ultraviolet sunlight and emitting green light. Except 3I Atlas was already analyzed in August by astronomers at Kitt Peak Observatory. They found it was among the most carbon chain-depleted comets known, possessing very low concentrations of diatomic carbon, the exact molecule creating green comets. How does a comet with almost no diatomic carbon suddenly glow bright green? Loeb suggested the color change might connect to the rapid increase in cyanide production detected by the Very Large Telescope. Cyanide compounds can also produce greenish colors under certain conditions. But that raises another question. Why is cyanide production increasing so dramatically? VLT observations showed hydrogen cyanide emission rising steeply as 3I Atlas approached the Sun. The production rate wasn't gradual like normal cometary outgassing. It was exponential, as if something was being thermally processed at accelerating rates. October 3, 2025. Tomorrow. The high-rise camera aboard Mars Reconnaissance Orbiter will point toward 3I Atlas as it passes 29 million kilometers away. 30 kilometers per pixel resolution, detailed enough to separate the nucleus from its dust cloud, detailed enough to measure surface area and constrain this object's actual size. If the nucleus confirms at 5 kilometers or larger, the statistical problem becomes impossible to dismiss. We should have discovered thousands of smaller interstellar objects before detecting one this massive. ESA's Mars Express and ExoMars Trace Gas Orbiter will observe simultaneously using spectrometers and cameras. Multiple wavelengths, multiple instruments, multiple perspectives. Between all Mars spacecraft, we'll capture the most detailed examination of an interstellar object ever achieved by humanity. And we'll search for precursor probes, objects traveling ahead of 3I Atlas that could reach Mars while we observe the main body. HiRISE will scan surrounding space. If anything appears that shouldn't exist, if multiple objects manifest instead of one, the conversation transforms immediately. Then comes the waiting period. 3I Atlas disappears behind the Sun from Earth's perspective in late September. We lose line of sight. The object reaches perihelion on October 30th. Hidden from our telescopes by 150 million kilometers of incandescent plasma. 2 months of blindness, 2 months where anything could occur and we wouldn't witness it. December 3rd is when ground-based telescopes expect to reacquire 3I Atlas. Amateur astronomers worldwide are preparing. Professional observatories are scheduling observation time. Everyone wants first confirmation of the object returning from perihelion. And everyone will be comparing post-perihelion observations to pre-perihelion data. Has brightness changed? Has outgassing increased or decreased? Most crucially, is it where calculations predict? If 3I Atlas emerges on a different trajectory, if its orbit has changed in ways unexplainable by gravitational interactions with the Sun and planets, that's evidence of propulsion, evidence of technology. That's when even skeptics will need to consider alternatives seriously. The chemistry will reveal more. Fresh spectroscopy in December will show whether the nickel without iron signature persists, whether carbon dioxide dominance continues, whether new emission lines appear absent before perihelion. If the object fragments, that actually supports the natural comet hypothesis. Natural comets sometimes break apart near perihelion from thermal stress. We've observed it with comets like Shoemaker-Levy 9 before it impacted Jupiter. Fragmentation would be expected. Unless the fragmentation appears controlled, unless multiple pieces separate cleanly and head toward different destinations, then fragmentation becomes deployment. March 2026 brings the Jupiter encounter. NASA's Juno spacecraft, currently in polar orbit around Jupiter, could potentially observe 3I Atlas as it passes within 54 million kilometers. Juno possesses cameras, spectrometers, particle detectors, instruments designed for studying Jupiter, but capable of characterizing this visitor. ESA's JUICE spacecraft will also attempt observations in November, though we won't receive data until February 2026 due to communication delays. By spring 2026, we'll possess the most comprehensive data set ever assembled for an interstellar object. That data set will either confirm 3I Atlas as an exotic but natural comet from another star system, or it will force us to seriously consider that we're being visited. The scientific community is preparing for both possibilities. Privately, astronomers are discussing protocols if technological signatures are confirmed. Who announces it? How do you verify extraordinary claims before disclosure? What are implications for planetary defense if more objects follow? There's no established procedure because nobody seriously anticipated this scenario. SETI protocols focus on radio signals and intentional beacons, not physical objects masquerading as comets. Some scientists advocate for an intercept mission. Launch a probe to rendezvous with 3I Atlas before it escapes beyond Jupiter's orbit. Capture high-resolution images, sample the outgassing plume, measure magnetic fields and particle emissions up close. The problem is timing. Even a fast spacecraft would require months to intercept. By the time authorization and funding materialized, by the time the probe was constructed and launched, 3I Atlas would be long gone. Interstellar objects move fast. Opportunities measure in weeks, not years. That renders this October to March window so critical. This is our opportunity, our only opportunity, to gather data on the third confirmed interstellar visitor before it vanishes back into the void between stars. After March, it will be too distant and too faint for detailed observation. We'll watch it fade, extract every possible information fragment from observations we managed to collect, and then wait. Wait to determine if our analysis reveals natural explanations for all anomalies. Wait to see if more interstellar objects arrive with similar characteristics. Wait to see if the statistical problem resolves or compounds. And we'll wonder, even if data ultimately supports natural origin, even if every anomaly finds conventional explanation, we'll wonder, because 60% probability of technology means 40% probability of natural processes, and 40% isn't zero. The universe has surprised us before. Black holes, dark energy, exoplanets, gravitational waves. Each discovery revealed phenomena we didn't predict and barely comprehend. 3I Atlas might be another surprise. Something natural but so unusual, so unexpected that it challenges our models and compels us to expand our understanding of what's possible. Or it might represent the most significant discovery in human history, first confirmed contact with technology from beyond Earth, evidence that we're not alone, proof that other civilizations exist and some achieve interstellar capability. We'll know soon. The data is arriving. October 3rd, December 3rd, March 2026, 3 dates that might change everything.